Okay, year 11. This is the model solutions for paper 2 and 58 marks, shorter experiment. So let's go through it. So question 1, largely just a fairly straightforward sort of set of recall connecting physical quantities up to their correct units and then identifying following. So that's pretty recall. Difference between scalars and vectors. Vectors of size and direction, scalars of size only. Any kind of that idea. And then any correct example of a scalar quantity, so speed, time, energy, distance, mass, temperature, absolutely fine. So it's a fairly straightforward thing. Okay, question 2. We have a pencil with a weight. What is the mass of the pencil? We've got to convert newtons into kilograms, and then we've got to convert that into grams. So we end up with B. And then we have a moments question. Okay, so we've got moments, we've got finger, we've got some balancing a pencil on a pivot, calculate the moment. So it's going to work through this one quite nicely. Determine the moment using the equation that we're given. So again, it's a case of substitute in, get answer 0.592. State the moment there for a force F, given that it's resting, so it's balanced, keeping it horizontal. Therefore, it's the same moment, so it's whatever answer you got here transposed to there for your 1 mark. Show that the force therefore is 0.080 newtons. Same equation but working in reverse, where we're given, we now know the moment, don't know the force, we do know the distance, so we can then rearrange it and get the answer. The reason that there are no marks here for selecting it, this is why they give you the equation here, because if you're unable to select the right equation, you can't do any of this question. So that's why they tell you which one it is to use, even though it's in the formula booklet. Okay, right, okay, so glass prism can be used to refract light. State the name of the piece of equipment you have. It's a protractor, which we know because a lot of you come asking for them before your maths exams. Then you measure the angle of incidence as an angle of refraction with your protractor. They give you a fairly large amount of leeway. I measured them about 44 and 28. That's my measurement that I'm using going forward in this one. But they allow anything from 42 to 46. So a couple of degrees either side is perfectly fine. State the formula, linking to work out the refractive index. And there we go. And then use it using the number that you've just you've just calculated. Given that your tolerance value, depending on which ones you picked, your value of n could be anywhere from 1.34 all the way to 1.64. That's where the range you could have if you use the numbers that I've got, 1.48. Okay. So it does say allow full credit for correct answer with no working. So if you just wrote 1.5 because you know that the refractive index of glass is 1.5, then congratulations, you get all the marks. Okay. So solid bar of chocolate taken from the refrigerator. We've got the temperature. Describe the arrangement and the motion of the particles. So our motion, say the particles can vibrate around fixed positions. That's our description of the motion for 1 mark. In a regular arrangement, that's our 2nd mark. So vibrating around fixed positions, that gets you the 1st mark. Regular arrangement gets you the 2nd. Chocolate's heated at a constant rate until the temperature reaches 45 degrees. The chocolate has a melting point of 32 and a boiling point of 55. So that's going to tell us, that it's a liquid. So essentially, this question is now, describe the motion of the particles now, and it hasn't told you it's a liquid, so you have to, determine that yourself. So you've just got to work out that it's a liquid, and then you can describe the motion of particles as a liquid. Again, particles move randomly past each other. Okay, so as they are no longer in a fixed position. So key terms here: they've got random motion as they move around, and they are no longer in a fixed. Position. That's how much, or they can move past each other. So they're no longer fixed. Oh, which of these is used to measure the temperature? Thermometer. Okay. Then we have a graph, 3 marks. Okay, use the axes to sketch a graph of how the temperature of the chocolate changes with time when it's heated from 5 to 45 degrees. What we know is that we have a melting point at 32, and we know that during a change of state, there is no change in temperature. So essentially, on this graph, we're going to start here, we're going to get up there, but at 32, so 25, 30, so at this temperature here, we are going to have some point, okay, when we are going to have some point where at 32 degrees we are going to have some sort of flat line. We've got a flat line that's there, and then we just need to connect in straight lines. So I'm going to hope I do this. Now it's a terrible straight line. Boo. And then a straight line like that. They're not worried about the gradients of the line. They are just as they are. So straight line, flat, straight line. So yeah, one mark here, one mark here, one mark here. Okay. Okay, question 5. So one I thought was a bit harder. So here's a magnetic field around a section of copper wire. Explain why the copper wire has the magnetic field shown in the diagram. So our first thing is that what causes the magnetic field? There is a current flowing in wire. That is what is creating the magnetic field, that there is a current. So that's our first mark. But what's interesting is this is a current, this is a field that's coming out and around our wire. Okay, so if this was in front of you, this wire, these field lines are coming around them in a particular direction. And you can find that out using the right-hand grip rule. Okay, if you have the right-hand grip rule, then you stick your thumb out and curl your fingers around. Your fingers curl in the direction of your thumb. So basically, the direction of the current in this case is going to the right. To get your fingers to curl like this, you have to sort of hold your thumbs pointed to the right, and your fingers will curl around in the same way that these wires are. So that is our second mark. Okay. So 1 for the actual identified as a current, 2 for identifying which way it's going. Okay, we have an experiment with electromagnets varying with the current, so how the current affects its strength. So we've got a method: switch on the electromagnet, place 100 grams on, reduce the current until it falls, record the current at which it falls, try it two more times, and repeat for loads of different masses, and suggest a suitable safety precaution for the investigation. Basically, there's 3 kinds of things. There's a falling hazard, both to you and to the floor. Okay, and there's also a heating hazard because you've got current. So pretty much anything that's going to minimize either of these things. Okay, so falling hazard is you could don't have feet underneath. Okay, some idea that something could hurt you if it fell on you, or it could damage the floor. Unless you might put some soft materials down. Heating hazard, the coil might get hot, so you could wear gloves. Okay, you are basically something that would indicate that you're aware these are the hazards. Very bland things like oh no, sorry, I've misread where the marks is. It says ignore that, so it doesn't. That is not okay. That would actually be apologies. That is allowed to cool. Apologies, I misread where the mark scheme was saying that earlier on. So anything that would solve these sort of problems. Okay. Let's go along. Where's my... Okay. We then got these results, and we are calculating a mean. We need to get to an appropriate number of significant figures. if you do the mean of these three, you get 1.8 with loads of threes recurring. If we look at all of our data is to this level of precision, so 2 decimal places. So our final answer is 1.83. So we just want to give that as our answer. If you give more or less, then you're going to drop a mark. You want to be consistent with everything in your table. On the grid, plot the graph. The scale has been done for you. Okay, so our marking points here, we've got marking points for like selecting a sensible scale here, which is kind of pretty obvious, and labeling it. So we've got to have a sensible continuous scale, which is labeled with current with the unit, and plotting the data correctly. So that gives us our markings. So we've got scale, label, and plotting. Each of those is giving you just 1 mark. I seem to have flipped my colours around. That's very nice. And then we have a drawing a line of best fit. So just so you're aware, it's a straight line, okay, as it is. And what they are after is a approximately equal distribution of points either side. So a line which would go above all of the points would drop the mark. So here you can notice I've got 1 that's on the line, 1 that's below, another sort of 2 on the line, and then 2 above. So you could argue I've got sort of 2 on one side, 1 on the other. That's approximately equal. That's fine. So there's a fairly reasonable amount of tolerance on there. It does not have to go in this case through the origin because you haven't tested that, so that's fine. And then we have 3 marks. The student makes a prediction. A load of 1 kilogram will fall when the current is 3 amps. Comment on the student's prediction. So there's quite a lot you can say about this. So, we can comment on, why are they, something that we would know, why are they correct? Okay, well, if we want to think about why they're correct, we can say that, well, 1 kilogram is equal to 1,000 grams. Okay, we know that. Weirdly, you get a mark for that recognition, which is, quite generous. We say, okay, they might be correct. 1 kilogram is 1,000 grams. Let's look at our table. Ooh, okay. We can say that that is double 500 grams. Okay. Oh, wrong color. So this is double 500 grams. 500 grams has 1.50 amps. Okay. So 1,000 grams has 3.00 amps. Okay, so we can sort of show this. Okay, this is actually a long way of just sort of getting 1 mark. There's lots of ways to do it in symbols, but essentially we're saying, oh, we've got double this, and so double that, we get 3. Why is that a reasonable inference to make? It's reasonable because this is a straight line through the origin. Okay, we can say this is fair. Okay, because mass is proportional to the current. Okay, we can say it's fair because this is a straight line to the origin. Okay, so we can talk about that symbol if you've not seen it before. Sorry, that is the word proportional. So if you say those 3 things, if there's the idea that you know that what a kilograms 1,000 grams, and you take one of them, you double it. You could take this one and times it by 5. There's lots of things you could do. And you would get this idea of 3 amps, and you could say, oh, okay, that's kind of like why those. However, you can also argue why this thing might not be. There are 2 marking points for why you might say this comment isn't correct. You can actually say that, however, 1 kilogram is is far outside the measured range. Okay, so that 1 kilogram is all the way, it's up there somewhere. Okay, that's where our measurement is. In order for that to be true, this line would have to continue, and we just don't know if that's true. Okay, the pattern may not continue this far. Okay, so we do not know. This may curve, this may do something else. So it might carry on straight, but we don't know. So you can make sort of a reasonable thing about the fact that this is worth 2 marks for a comment on the fact that you're taking that prediction way beyond the limits of your experiment, which isn't always true. So as you may have seen with like Hooke's law, like it's not eventually the spring breaks, eventually things might change, and so we have to be aware of that. It's not really an important thing about whether this person's right or wrong. It's what you think is reasonable to say about that conclusion. Okay. Right, question 6. We've got some momentum calculations, so fairly straightforward. First thing is we've got some information about a bird and its mass. We'll show the momentum is about 5 kilogram meters per second. Momentum is mass times velocity. So we're getting a mark for our putting that in. Get a number 5.33, which is about the same. You don't need to then write that is approximately equal to 5 kilogram meters per second. Okay, now just so you're moving on to this next bit, you can either work through the rest of the calculations with 5.33, so the number that you've worked out, or with 5. The mark scheme has both. I've done it using 5.33. You can always do it with 5, but it's still completely fine. So you've told the momentum of bird Y is 0.15. Therefore, what's the total momentum? You just add it together. So it's 5.33 plus 0.15. State the total momentum just after they've caught just after bird X has caught bird Y. It's still 5.48. They're moving off together. And then bird Y has a mass. Calculate the velocity of the birds just after bird X has caught bird Y. So you get 1 mark for working out the total mass because we've got bird Y's mass and we've got bird X's mass. So we're going to add them together to get 0.58. We're taking the momentum that we've had, which is 5.48, and then we put it back into the same equation. Momentum is mass times velocity. I've got momentum is mass times velocity. So we can do a substitution, and then we can get our calculation. So we rearrange and calculate. You get 9.45, or slightly less if you've used 5.15. Perfectly fine. Okay, and then we have our last couple of questions to do. Question 7. Right, okay. We've got concrete on top of buildings can be used to heat water. This is a water heating system being built into the roof of a house. Okay, so this picture, utterly irrelevant to the to most of the rest of the thing. So a scientist wants to determine the specific heat capacity of concrete. The diagram shows some of the equipment they could use. This is an experiment you did in year 10. Describe a suitable method to find the specific heat capacity of concrete. This mark scheme here is enormously generous. There's a lot of stuff that we could say. So ultimately, we're trying to use, we're trying to use 2 equations. We're trying to use the equations that we're using electrical heater. So we've got energy is mass times specific heat capacity times the change in temperature, and energy is equal to current times voltage times time. They're the 2 equations we're going to link together in order to determine C, that thing. Okay, so let's think about the things that we want. Okay, first off, well, we need to know our mass. What do we measure mass on? A balance. Okay, so measure mass on a balance. That's not anywhere in our equipment, so we're going to get a mark for that. Okay, we are going to also need to measure time. There's nothing in our picture that tells us what the time is, so we're going to measure time on a stopwatch. Okay, or a timer or a stop clock or sort of anything. Okay, we need to know what this is, our delta T. So our change in temperature is final minus initial. Okay, so the idea, we need to sort of like, take, we need to measure those, we have to work out what the change in temperature is. Okay, our fourth mark, okay, is sort of like, actually we're going to get, there's a mark for sort of like stating this equation. This is our energy supplied, this here. That is our sort of fourth marker. I find it easier to think about the equation first. And then they're going to give a mark. This equation as it is in the exam, is in this formula sheet. So they want you to rearrange that for a thing. We're trying to work out C. So so we would actually say that heat capacity is equal to energy over mass times change in temperature. And we know that energy is current times voltage times time. So we can combine that to get current times voltage times time over mass times change in temperature. So we've now got the way of working out our, we've now got the way of what we're going to do to work out our thing. So this, okay, so if we essentially do this, measure mass and balance, measure time on a stopwatch, calculate the change in temperature using final minus initial, okay, and we can use this, we're using this equation, this rearrangement, and then we're combining it to get this. So we, just so you're aware of the mark scheme, it's allowing us to give a mark for this, a mark for this, a mark for our working delta T, a mark for knowing this equation, a mark for rearranging this equation, and a mark for combining it. Okay, we now have the ability to get our, you can add other things. We're reading magnitude in the volt. We're reading, so we can put out V. We're going to read from voltmeter. Current is read from ammeter, although there's no marks for this. Okay, we now have all the things, and essentially what we need to do is, we can turn on heater for 2 minutes. Record values. Values and calculate C. Okay, so essentially that's what we're going to do. And at the end of it, I am going to repeat and average the experiment. Okay, so there's a lot of marking points. There are some more in the, there are some more in the mark scheme, but this gives you everything you need to do to determine the specific heat capacity. So there we go. I think there's 10 marking points in the mark scheme, and you are after any 5. So explain the advantage of the concrete having a high specific heat capacity when it is used to heat water in the heating system. Well, a high heat capacity, okay, means that you can store a lot of energy. Okay? So because if you have to put, the higher the heat capacity is, the more energy you have to put in to raise the temperature. So that energy is stored in the block as a thermal energy store. So it's just holding on to more energy. So it's high specific heat capacity stores more, storing more energy. Okay. So if we've got more energy, that means that this water that we're trying to heat up we can just heat it for a longer time because we're holding on to more energy. Okay, so water can be heated for a longer time. And they're sort of your two sort of key marks there of recognizing what it means to have a high school heat capacity, and therefore you can heat stuff up for a longer time. Okay. And final question, which is to do with sound. We've got sound waves. Pick things that can be heard by humans. So the human range is 20 to 20,000. So essentially, yes, we can hear, we can hear. We cannot hear the top two. Okay. Do try and avoid putting crosses and ticks in something. If they only ask for ticks, just do ticks. Just make a mark in the box that you want a mark to be in, or leave it blank. Okay. So if you make a mark in either A or F, you get 0. If you make a mark in, if you only mark C and D without marking A and F, you get 1 mark. So, right, okay. So here is an oscilloscope. Okay. Add to the diagram. Okay. So here is an oscilloscope when a sound wave is detected. Add to the diagram, we're drawing the trace of another sound wave that has a lower pitch and is quieter than the sound shown below. So things that we know is that if it's quieter, okay, so lower pitch, okay, and quieter, that means smaller amplitude. Lower pitch means a lower frequency, which means a bigger time period, so the waves are spread out more. So okay, so we're going to spread things out with so anything which has a lower amplitude and a lower frequency, so something like this would be fine. Anything of this sort of thing is absolutely fine. So any trace which is both lower and more stretched out. Okay, and finally, final question. It's back on. Calculate the wavelength of a sound wave. So we've got the speed of sound varies with temperature. When the air temperature is 46 degrees, the speed of sound in air is 360 meters per second. Okay, so I've got that. And that's V. Calculate the wavelength of a sound wave with a frequency of 15,000 hertz. So essentially, and I forgot to do this one beforehand, so we're just using V equals F lambda, which is 1 mark. We're going to put our numbers in, so we've got 360 is equal to 15,000 times lambda, and so we can then solve that. That's our second mark. We get a solution of 0.024, and that is our final calculation, and that was the extension paper.